Welcome to The Explainer. Today, we're going to pull back the curtain on how your favorite apps and websites find information so ridiculously fast. And it all boils down to one simple but really powerful idea: the binary tree.
So let's kick things off with a problem we all get. Imagine a massive library, like millions of books, but there's no catalog. And you need to find one specific book, right now. How in the world do you find it without spending the rest of your life looking? That's the exact problem computer scientists are trying to solve every single day.
Now, if all your data is lined up nicely, sorted like words in a dictionary, there's this amazing trick called a binary search. You don't start at page 1. No way! You jump straight to the middle. Is your word before or after that middle point? Just by answering that one question, you get to throw away half the dictionary. You just keep doing that, chop it in half, again and again, until you land right on the word you need. It's so efficient, it almost feels like cheating.
But here's the catch. Real-world data is rarely that simple. What happens when it's not in a straight line? What if it's messy with branches and all these complex relationships, like a family tree or even the files and folders on your computer? That simple binary search trick it doesn't work anymore. We need a whole new kind of structure.
So to handle that kind of branching data, we need something that looks less like a line and, well, more like a tree. And this brings us to one of the most important, most fundamental tools in all of computer science, the binary tree.
Okay, so what makes a binary tree binary? Well, while a regular tree could have a whole bunch of branches coming off one point, a binary tree has one simple, powerful rule. Each piece of data, we call it a node, can have at most 2 children. That's it, a left one and a right one. And that one little constraint makes them way easier to work with.
So to really get how these things work, we gotta learn the lingo. Let's just quickly break down the vocabulary using this classic picture of a binary tree.
Everything kicks off at the root. That's the one node at the very top. Any node that has branches underneath it is called a parent, and the nodes they connect to are its children. And see those nodes at the very bottom, the ones with no kids of their own? We call those leaves. Finally, each horizontal row of nodes is just called a level. Pretty intuitive, right? It's just a way to map out a hierarchy.
All right, now that we've got the basic terms down, you should know that not all binary trees are created equal. They can come in a few different shapes. So let's take a quick little detour to look at 2 really important types: full trees and complete trees.
First up is a full binary tree, and the rule here is super strict. Every single node has to have either 0 children, which makes it a leaf, or exactly 2 children. No lonely single children allowed. Then you've got the complete binary tree. This one is all about filling up the tree perfectly, level by level, always from left to right, with no gaps.
And you can really see the difference here. On the left, that's a full tree. See how every node that's not a leaf has precisely 2 children? Perfect. The tree on the right, though, is not a complete tree. See that gap on the last level? To be complete, that spot would have to be filled in. So just remember, full is about the number of kids, and complete is all about the filling order.
Okay, so a regular binary tree is a great way to structure data. But on its own, it doesn't solve our original problem: how to search fast. For that, we need to add a little bit of intelligence to the structure.
And this brings us to the main event, the real star of the show, the binary search tree, or BST. The whole secret is in the name. It's all about the order. A BST takes that simple binary tree structure and adds one single, elegant rule that completely changes the game.
And here it is. This is the magic rule. For any node you pick in the tree, everything in its left subtree has to be less than it, and everything in its right subtree has to be greater than it. That's it. This one simple idea is what unlocks all of that incredible speed.
Let's actually build one really quick to see this in action. We'll start with the number 10. That'll be our root. Now let's insert 5. Is 5 less than or greater than 10? It's less, so it goes to the left. Easy. Next, 13. That's greater than 10, so it goes to the right. Now it gets interesting. Where does 8 go? Well, we always start back at the root. 8 is less than 10, so we go left to the 5. But wait, 8 is greater than 5, so it becomes the right child of 5. See that? You just apply the same rule over and over. One more, 16. It's greater than 10, so we go right. It's also greater than 13, so we go right again. And it finds its home.
Okay, now for the payoff. Let's search for the number 13. We start at the root, which is 10. Is 13 greater than 10? Yes. And right there, that single comparison tells us that we can completely ignore the entire left side of the tree. Everything over there is smaller, so our number can't be there. We just threw out half our data in one step.
So we move to the right and, what do you know, we're at 13. Found it. 2 steps. That is the power of a binary search, but in a tree.
So what does this all mean for performance? Well, with the regular binary tree, if you're unlucky, you might have to check every single node. That's what we call ON time, and it can get really slow. But with a balanced binary search tree, the search time grows incredibly slowly. You could double the number of items in the tree, and it would only take one single extra step to find anything. That's O log n, and trust me, that is unbelievably fast.
Now, this might sound like some abstract computer science lecture, but I promise you, its impact is absolutely everywhere. So, why does this all matter in the real world?
You might not actually see them, but you are using binary search trees constantly, every day. Every single time a database pulls up your info in a split second, that's a BST-like index doing the heavy lifting. When you start typing into a search bar and it instantly suggests what you're looking for, that's a tree structure, finding all the possible matches in milliseconds. It is the hidden engine behind so much of the high-speed tech we all just take for granted.
When you think about it, the binary search tree is just this beautiful example of how a very complex, powerful system can come from one ridiculously simple rule. Left is less, right is greater. All that efficiency, all that speed, born from that one idea. And it kind of makes you wonder, doesn't it? What other huge, complicated systems, maybe in technology or even out in nature, are built on top of a single elegant principle just like this one?